Frames of reference. In this lesson, we're going to be talking about relative motion, some applications, a couple of examples, and then some practice problems. Relative motion. So what does it mean, relative motion? What does relative motion actually mean? When discussing the motion of objects, we need to give a frame of reference. So if an object is moving, we need to give a reference of what is it moving relative to. So for example, if you have two animals, so let's just say we have a sloth, and excuse my drawings, so that's our sloth, and then we have a turtle. Right? Now the sloth moves really, really slow, whereas a turtle just moves slow. So relative to the sloth, the turtle actually moves fast, or at least faster, right? Now, if we do the same situation and we put the turtle here and we put the sloth on top of the turtle, so the sloth is going to go for a little ride on the turtle. Now, since the turtle moves faster than the sloth is going to feel like it's actually going fast. So relative to how it normally moves when it's riding the turtle, it's going to be moving at a pretty quick clip. So let's consider this example here. We have two friends. Jay is going to be on the left escalator. So here's Jay. That's Jay. And Sue is on the right escalator. Here's Sue. Both escalators are stationary to begin with. The right escalator, Sue's escalator, begins to move downwards at 0.62 meters per second. Remember, Jay is still stationary. So how fast does Sue need to move in order to not move relative to Jay? Well, if she's moving down at 0.62 and Jay is stationary, she needs to start walking up the escalator at 0.62 meters per second. When she does, then she's going to have a net velocity of 0 at that point. So relative to Jay, her velocity is going to be 0 at this point when she starts walking up the escalator at 0.62 meters per second. Now the second part, if Jay begins to walk up the stairs at 0.34, let me just make some room right there. So he's going up the stairs at 0.34 meters per second. How fast does Sue have to move in order to keep up with him? Well, Sue, let's just say that up is positive. Okay, so initially Sue has a velocity of negative 0.62 meters per second. We need her to move actually positive 0.34. So we need to make up the difference. So it's going to be 0.34 subtract negative 0.62. Two negatives, you add them together, and you get a velocity going upwards of 0.96 meters per second. So if she wants to keep up with Jay, who's moving up the stairs at 0.34 meters per second, she needs to move 0.96 meters per second up. So more on what we mean by motion is relative. Well, if a person is standing still, they're actually moving at 1,600 kilometers per hour relative to a frame of reference at the center of the Earth, because of course the Earth is spinning. So the Earth is spinning, right? And relative to the center of the Earth, the person on the outside is actually moving at a really, really fast rate. In fact, it's 1,600 kilometers per hour. The center of the Earth is moving relative to the Sun at a staggering 110,000 kilometers per hour, because the Earth is rotating around the Sun, right? The Sun's going to be out here, and the Earth, of course, is traveling around the Sun. And the speed that it travels is 110,000 kilometers per hour. The Sun itself is moving relative to the center of the galaxy at an incredible speed. So it's rotating around something as well. So this explains why when we're driving, so let's just say we're driving to the right at 100 kilometers per hour, and maybe you're on a highway, and you see a car going the other way at 100 kilometers per hour. It appears that they're coming really, really, really fast. Too fast, right? It appears that they're actually coming at 200 kilometers per hour. So this is our relative velocity. We'll say relative velocity. It appears like they're coming at us at 200 kilometers per hour, and we'll just say at us, AU, at us. It appears actually that you are stationary and that they are moving towards you at 200 kilometers per hour. And this is the phenomenon because of relative motion. They are moving towards you, you're moving towards them. It appears like they're moving towards you at an incredible rate, and in fact, you're actually just standing still. Relative motion. Suppose a large boat is moving at a velocity of 5 meters per second south relative to the shore, and a passenger is jogging at a velocity of 3 meters per second relative to the boat. Relative to the shore, the passenger's velocity is the addition of the two velocities. So 5 meters per second south and 3 meters per second south, or 8 meters per second south. And this makes sense. So if our boat is moving this way at 5 meters per second south, and we have someone on board running along the boat at 3 meters per second south as well, it will appear to somebody over here that this person is actually moving at the addition of the two numbers. So it appears that they're moving at 8 meters per second south, or in this case, right towards them, because you're going to get the motion of the boat plus the motion of the person. So in this case, the shore is one frame of reference and the boat is another frame of reference. Relative motion. To analyze relative velocity in more than one frame of reference, we use the symbol for relative velocity, with two subscripts in capital letters. The first subscript represents the object whose velocity is stated relative to the object represented by the second subscript. So what does that mean? Well, in other words, the velocity of the first letter is being measured or observed from the second letter. This is the frame of reference. So regarding the velocity of the person on the boat, the velocity is going to be measured from the reference point of the person relative to the shore. And that's what we have here. And that's going to equal 8 meters per second. And this means that the person, P, is jogging at 8 meters per second south relative to the shore. And that's the VPS. So the first letter is the thing being measured, and the second letter is what it's relative to. Relative velocity symbols, the boat example. So in this case, we can break down our symbols into all the different combinations. So we're all going to have the velocity. So it's always velocity for V, right? Same thing, same thing. VBS is going to be the velocity of the boat relative to the shore. So how fast is the boat going relative to the shore? VPB is going to be the velocity of the person relative to the boat. And VPS is going to be the velocity of the person relative to the shore. And this is our equation right here. So in our previous example, the velocity of the person relative to the shore is going to equal to the velocity of the person relative to the boat plus the velocity of the boat relative to the shore. So we get 3 plus 5 equals 8. So suppose the passenger in the boat example previous is jogging at a velocity of 3 meters per second east. So let's draw our symbols out. So we're going to go 3 meters per second, and we're going to say that that is east, and we're going to call that positive. And you know what, to make our math easier, let's do east, south, and we'll make that positive. So the person is jogging at 3 meters per second east relative to the boat, so that's VPB, so that's velocity of the person relative to the boat equals 3 meters per second. As the boat is traveling at a velocity of 5 meters per second south, so 5 meters per second south, and this is going to be the velocity of the boat relative to the shore. Determine the jogger's velocity relative to the shore. So what that is, it's actually this one right here. It's going to be the hypotenuse. It's going to be the result of the two vectors, just like we were doing before. So how do we figure out what the hypotenuse is? Well, the velocity of the person relative to the shore is going to equal to the square root of 3 squared plus 5 squared. And that equals to 5.83 meters per second. We need an angle. So just like we were doing before as well, theta is going to equal to tan inverse opposite 5 over 3. And that equals to 59.0 degrees. Now I'm actually going to put this 5 over here just to make it a little bit more simple. So velocity of the boat relative to the shore is 5 meters per second, and that should help clarify what that means. Okay, so what is the total velocity? Well, we need two sig-digs in our answer, so let's make sure we keep consistent. So our final answer is going to be 5.8 meters per second. And in this case, we went east 59 degrees south. And that's our final answer. The airspeed of a plane, so this is the velocity of the plane relative to the air. So we'll go velocity of the plane relative to the air is 215 kilometers per hour, and it's 34 degrees east of north. So we can draw that out. So east of north means it was going north, and then we went 34 degrees east of it. So that's going to be this right here, 34 degrees. The wind is blowing at 57 kilometers per hour east. So we're going to go like that. And we're going to say that that is 57 kilometers per hour. And we'll put in our 215 kilometers per hour right there. Determine the velocity of the plane relative to the ground. So velocity of the plane relative to the ground is going to equal to the velocity of the plane relative to the air plus the velocity of the air relative to the ground. So we need to add our vectors. So we need to break them into components like we were doing before. So we'll draw our verticals, and we'll use green for horizontal. And of course we have a green one there as well. Okay, so let's find our y components first. So our y components are going to be this first one here on the left. So it's going to be a component of 215. So it's going to be 215. It's adjacent, so we say cos 34. And before we go any further, let's set our positives as east and north. So 215 cos 34 is going up, so we're good. And then plus 0 because, of course, on the 57 east, there's no vertical component. So we add 215 cos 34, we get 178.2 kilometers per hour. For the x component, it's going to be 215, it's going to the right, so it's positive, sine, because it's opposite, 34, plus 57. When we put that into our calculator, 215 sine 34 plus 57, we get 177.2 kilometers per hour. So now we can draw our triangles again. So just like we did before, first we're going to go up 178. We have to make our triangle a little small so we keep enough room here. So we'll say like that, and we'll say that that's 178.2. Then we need to go to the right, 177.2, and then our hypotenuse is going to represent the velocity of the plane relative to the ground, and that's going to be the square root of 178.2 squared plus 177.2 squared, and that equals 251.3. We also need an angle, and we'll say theta is going to equal to tan inverse opposite 177.2 divided by 178.2, and that equals to 44.8 degrees. So our final answer, we need two significant digits. It's going to be 250 kilometers per hour. We're going to go north 45 degrees east. And that's our final answer. A ship is moving with a velocity of 2.8 meters per second forward relative to the water. So let's just do forward as positive. Draw our vector in, and we'll say 2.8 meters per second forward relative to the water. A group of people walk on the deck with a velocity of 1.1 meters per second relative to the deck. Determine their velocity relative to the water if they're walking towards the starboard. The starboard is on the right-hand side of the ship as you face the front. So if they're walking to the right side, we can draw them going this way. Because we said that the boat was going, in our case, to the right. So we can say that they are going down, and we'll say 1.1 meters per second. So this is going to equal to the velocity of the people relative to the boat, and 2.8 is going to be the velocity of the boat relative to the water, 2.8 meters per second. And our question is asking for determine the velocity of the people relative to the water. That's our question. And velocity of the people relative to the water is going to equal to the velocity of the boat relative to the water plus the velocity of the people relative to the boat. So it's going to be a vector addition question. We're going to follow the exact same format. We're going to say that the velocity of the people relative to the water is going to equal to the square root, 2.8 squared plus 1.1 squared. And that equals to 3.01 meters per second. We need theta. Theta is going to equal to tan inverse opposite 1.1 divided by 2.8. And that equals to 21.45 degrees. We need our answer to 2 sig dig, so we're going to say 3.0 meters per second. In this case, we're going to go forward 21 degrees and then starboard. And that's our final answer. A plane traveling with a velocity relative to the air, so velocity of the plane relative to the air is 320 kilometers per hour, 28 degrees south of west. So what does that mean? Well, we were going west. We went 28 degrees south of it. So it falls in here, 20 degrees south of west, and that's 320. Passes over New York City. The wind velocity is 72 kilometers per hour south. So our second vector is going to go south, and it's going to be 72 kilometers per hour. Determine the displacement of the plane from New York City 2 hours later. So it's a little bit tricky, right? Because these two numbers are in kilometers per hour, and we're being asked for displacement. So what we need to do is we need to figure out the resulting velocity, the velocity of the plane relative to the ground, and then from there, we can figure out the displacement 2 hours after. So the velocity of the plane relative to the ground is going to equal to the velocity of the plane relative to the air plus the velocity of the air relative to the ground. So we can do our vectors. Just like we've done before, we need to find a vector addition here. We're going to take our x value going left, and we'll take our y value going down and down. And in this case, we're going to say that left and down are positive values. That's south and that's west. So let's figure out our x's first. Our x's, we only have one x. So we're going to say it's 320. We said left was positive, so that'll be positive. 320 cos because it's adjacent. 28 plus 0 because the second one doesn't have an x component. So 320 cos 28 equals 282.54. Then we're going to take a look at our y components. They're both going down, so they're both going to be positive. We're going to have 320. It's opposite, so we're going to say sine 28 plus 72. So 320 sine 28 plus 72 equals 222.2. So now we're going to draw our triangle. We're going to go left and down. So we'll go left, 282.54, and we're going to go down 222.2. On the hypotenuse, that's going to be our velocity plane relative to the ground. So velocity of the plane relative to the ground is going to equal to the square root 222.2 squared plus 282.54 squared. And that equals to 359.4. We need an angle. So theta is going to equal to tan inverse opposite, which is 222.2 divided by 282.54. And theta is going to equal to 38.2 degrees. So our final answer to 2 sig digs, velocity of the plane relative to the ground, is going to equal to 360 kilometers per hour. Then we're going to go west. So we went west first, 38 degrees south. So we went west and then south. And that's our final answer. And that concludes our lesson on frames of reference.